Big Apple Academy, where excellence becomes tradition.
And have you ever done this experiment? Probably, right? I'm going to take the balloon and I'm going to let it go. The balloon's going to go in one direction, but what's the air going to do? It's going to go the other way, which is why you get motion with this law. Every action in equal and opposite reaction. 3, 2, 1, and off it goes. But that's not so exciting. Let's try the exact same experiment with this. What's this? This is a fire extinguisher, right? Filled with lots and lots of CO2 under very, very high pressure. Lots and lots of force. I'm going to take all the force in this fire extinguisher, and I'm going to go ahead and I'm going to hit that sail right there with all that force. Now, as you're watching, I want you to tell me, what direction does my cart then go in when I do this experiment? Hey, you don't have to, I won't know what you're thinking, but think to yourself. But let's do a physics survey. Who thinks I'm headed that way? Who thinks I'm headed that way? Who thinks I'm headed this way? Who thinks I'm going that? Well, sooner or later. Not today, I hope. By the way, this is going to be an extremely loud noise, so let's see what we get here. And it's just like a grenade. You actually pull the pin. There's that much force in here. So let's do our experiment, all right? 3, 2, 1. Which way did I go? Nowhere. The only thing that happens is your butt gets really cold because it goes right down your shorts. Now, why? You saw and heard how much force I put on that sail, but there's no actual motion. Of course not. You don't push on yourself and go into motion. That's not how this law and rule works, right? In fact, what do we have to do? Well, this is why we have Ryan. Because Ryan is now going to stand directly behind me, sound headphones on, with that sail. And all the force of this fire extinguisher is going to come out and hit that sail now, but it's not attached to that cart anymore. What direction is this cart now going to go in? That way. That's obvious. But let me ask you this. Does Ryan have to be behind me here with that sail for me to go forward? And the answer is no. Right? There's nobody in outer space standing behind rockets. That's a lousy job to have. But we gave this job to Ryan because we want you to see how much force is on me and him as we do our experiment, okay? So you can see us both for a second, but let's see some rocket motion in action. 3, 2, 1. This right here in this container is water. Does anybody know what that is? Well, that's just regular soda, right? Regular Pepsi. Does anybody know what that is? That's Diet Pepsi. And I bet most of you have picked up one of these, or maybe even picked up one of these. But here's my question to you. You know what water is. You know what soda is. Does this can of regular soda sink or float in the water bath? Well, what do we do to find out? Let's do the experiment. So I'm going to put it right here in that water bath. Let it go. You'll note it goes right to the bottom. Right? I don't know how many predicted that, but that's exactly what happened. Right here, we have a can of diet soda. Does this sink or float in the water? What do you think? Let's say you try it at home. No, I'm going to do it right here. Let's do that experiment right here. I'm going to go ahead and put it in a water bath, and actually, it floats. Now, how would that be? It's kind of surprising, right? Because they give you the same amount of soda, they give you the same amount of bubbles, so why do they have a different density? Because that's why things sink or float. It's the density relationship. Well, this soda down here is sweetened with sugar. And that sugar soda, if you take that sugar out, there's a good almost an inch or inch and a half of sugar inside that can of soda. That's what you're drinking. Yum, yum, yum. It really has a high density comparison to this soda, which is sweetened with something we call NutraSweet. You just need a little bit of that really powerful chemical to make it as sweet as all that sugar. So this is more dense. This is less dense, as you can see. But has anybody here ever been in a swimming pool? And I bet the answer is yes. No. And anybody watching, have you actually been in our ocean? Again, I bet the answer is yes. And where do you feel more of a buoyant force lifting you up? Well, in the ocean. Why? What's in the ocean? Salt, sharks, toilet paper, lots of stuff. So if I take some salt and I pour it in a water bath, we see that that brings that soda right to the surface, just like so, just like that. Because now it changed the density of the water bath, and in sinking and floating, it's all about the relationship of density. That's exactly what we've done. Make the water bath more dense, it comes to the surface. But what floats in our air? Balloons, right? You ever have a birthday? What do they give you? They give you a helium balloon, right? And what I have right here is a helium balloon. You know what I'm going to do to that helium balloon? I'm going to pop it. I am. But I'll explain to you a little of the fun facts about helium, because when I pop that helium balloon, here's what's going to happen to the helium. The helium is going to leave this area right here. It's going to leave this building. It's going to go all the way up to the top of our atmosphere and then leave the Earth. It turns out that helium isn't held to the Earth by Earth's gravity. Earth's gravity is not strong enough, so any helium in our air winds up in outer space. And if that's all true, and it is, where did human beings actually first see helium? Well, it turns out it was also outer space. It was actually on the sun. In fact, helium is named after the sun. Helium, helios, that's why it's called that. It's named after the sun. We saw these burning yellow lines, these yellow-colored lines, and that told us there was a gas on the sun that we didn't know about. And then we looked here on Earth for that same gas. Where do we get our helium from now? And don't say the party store. It turns out that it comes from underground. When they pull gas from underground, a whole lot of helium comes with it. But we waste most of it. In fact, most helium winds up in outer space that we pull out of ground. In fact, we actually have a shortage of helium right now. Pretty dangerous shortage, because we use helium in quite a few things. But let's send more out to outer space and say goodbye to a little bit of helium, right? Let's see what happens when we light this balloon. 3, 2, 1, pops it. But we have a whole nother gas right here that floats a whole lot better than helium. And we're never, ever, 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 ever going to run out of this gas. So with helium being in a shortage, why don't they give you hydrogen balloons? I'll show you. So I'm now going to light this balloon, and you're going to see the difference between helium and hydrogen. For this, we'll turn the lights out. Wow. Let's see if you can keep your eyes on this hydrogen balloon. 3, 2, 1. An amazing sight, isn't it? Now, oh, thank you, Michelle. Here's what I got. What's this right here? This is a garbage can, right? It's a garbage can. What's it have on one side? It's got a hole. What do I have on the other side? I got some rubber right here. So more than anything else, this is like a big drum, right? And I can take this, I can hit bottom, but you don't actually see anything happen there. So you don't really know that anything's happening when I do that. You know, in physics, and I actually think in science and life, you want proof of things, right? You want to see what something's doing before you believe what someone tells you, right? Don't just believe what people say. Look for some proof. So Michelle, she's got a candle, right? And a lot of times in science, we see action at a distance. We don't really see what's going on, but we see what the thing does, right? So let's see what we can do with this, because with my garbage can, I can, let's see, blow the candle out. So you can see that this is actually doing something. But you still don't see exactly what's happening with our garbage can. And in physics and in science, what we like to do more than anything else, see exactly what's going on. So let's see that, because what I have right here is some theatrical fog. Now, theatrical fog is this glycerin that we heat up. It becomes a fog. They put glycerin in all your food, they just don't tell you. So no, we're not worried about this stuff. But it will show us exactly what's happening every time I hit the bottom of this garbage can. And this, to me, is one of the reasons why science is so much fun. What do we got? We got that smoke ring coming right out at you, right? And look how simple this is to make. And I dare you to go home and build one of those. That's what we have coming out of here all the time. But you didn't know it until we put the fog inside. And that's the fun part of science, seeing exactly what happens. Now, Ryan's got another object for me over here. What's that? That's a square. What's this shape again? That's a circle. So let's take our square. Thank you, Ryan. I'm going to take that square. I'm going to put it right here on the front of our garbage can. You here watching, tell me, tell your friends, what are we going to see next? Circles? Squircles. What kind of shape will come from our garbage can? I say we now do this experiment again. And for this, I'm going to add a little more fog. Let's put a little more fog in here. Good deal.
Circular prism.
So did you predict? That's what you have to do in science. You want to come up with an idea. Come up with a theory. What will we see coming out of here now? Squares or circles? Do the experiment. I do it, and you'll know it's actually still that smoke ring. A smoke circle. Now, why is it not a smoke square? Well, smoke squares are like unicorns. You want them to be real, but they don't really exist. The stability of our smoke ring is very different. You can't get that same stability in a smoke square. It doesn't happen, okay? It just won't exist. It won't stay stable for long enough to propagate across. So that's exactly what we have with air. But, you know, we've been playing in the lab a little bit. And Ryan here has a whole nother shape, the ellipse. What Ryan is now going to do is take the square away, and I'm going to take this ellipse, I'm going to put it right here on the front of the garbage can. It turns out that something rather special happens when we use the ellipse. In fact, one of the things we just discovered in physics, cosmology, is that gravitation waves move across our universe. It turns out when I put an ellipse on here, these gravitation waves look pretty much like what you're going to see right here. An oscillating ellipse coming right towards you, back and forth, as that comes out of there. And that shows you can actually do modern cosmology with a garbage can. How much fun is that? See if you can answer this question. How big is that sound? It's actually a pretty good question, right? Because we don't really know. We know how loud a sound is, how low a sound is. We measure sound through decibels, but we don't measure the size of sound usually as human beings. Why not? Because we don't see sound as human beings, right? You don't really know how large it is because that's not how we measure it. We're not with our ears. We basically have to see something to know how large it is, right? So we know an elephant is really large because we can see the elephant. We know a mouse is really small because we can see the mouse. And you don't see this sound. Or here in our show, we're going to show you exactly how large this is. And how am I going to do that? Well, I'm going to use fire, of course, and you knew that already. Just like that, I'm going to make this a nice even flame, just like this, right across the top of our tube. And now what I'm going to do is I'm going to put that sound energy back inside the tube. And when I do that, we see the size of that sound. That's exactly how big this sound is. And it looks just like a rope slinky, doesn't it? As a wave motion going up and down and up and down and up and down. If you could see that wave of sound coming to your ears right now, you would see that. And it's beautiful, right? And it's just a wave motion and kind of fun to see. Here's what we can do. I can change the tone of the sound. I can go higher in pitch, right? And when I do that, I want to ask you, what happens to the size of our sound? Well, I say we do the experiment. Predict to yourself what's going to happen, and then see it. Higher sound, smaller wave. And I can go lower in pitch. And when I go lower, you see we have a bigger wave, right like that. So the low waves in sound, they're big waves. The high frequency sounds are small waves, as you can tell with our flame tube that we have right here in front of you. All right? But this is just one tone we're putting in our tube. And what might be fun is instead of using one tone, is to use a song. And I know you all have your favorite songs. I realize that. And you know what? I'm not going to play any one of them. Instead, I'm going to play a song that you might hear if you've ever been in a wedding. Let's see if you can hear this song. and see the dancing waves of a song in our flame tube. There you go. And you can see that the tube reacts by giving us that large wave, and now all these different ones, the dancing waves of a song in the flame tube. And that's exactly what we have in this. It's a beautiful example of the waves that you can have inside and how you can see all those different waves. In physics and in science, when we discuss temperature, we're really discussing energy. We really are. We think of high temperature as high energy, low temperature as low energy, right? We think of a thermometer as an energy scale. And what I have right here in my hand, well, this is nitrogen. But this is nitrogen at minus 300 degrees. So it becomes a liquid at minus 300 degrees. And you can see it's kind of steaming out the top. And as I pour it out, it hits the floor and expands quite a bit. It turns out the nitrogen expands to 700 times its size from a liquid to a gas. And like we say, this is low temperature, but again, low energy. So anything I put in here loses its what? Its energy. So that's what we want to see right now. And the most common question I get from people when I do shows, and I do a lot of shows, they all say to me, hey, what happens when you put your hand in the liquid nitrogen? Well, I'm not going to do that. Instead, I'm going to do this. What's this? This is a hot dog. And am I a hot dog or what? Oh, yeah. And this is a room temperature hot dog, right? It's not frozen or anything. About the same temperature as me. If I press on a hot dog, it just crushes. And that's exactly what would happen to my body, my hand, if I pressed on it hard enough. It just crush. I'm meat just like the hot dog, so it would crush. So if I take a hot dog and I leave it in the liquid nitrogen for a period of time, this is exactly what happens to the hot dog. This is a minus 300 degree hot dog, all right? You can see the steam coming off the hot dog, but you can also note that this is exactly what would happen to my hand. Smashes and crushes just like that. I could do the experiment twice. I got two hands. I couldn't do it again. So people see me use this stuff in shows, and usually after a show, a child will come up to me and say, hey, where can I buy myself some liquid nitrogen? I'd love to have a little bit of fun with this stuff too. No, you don't want to play with this stuff. It's actually really dangerous. But I can do this. I can pour the liquid nitrogen right over my hand like that. You notice that the liquid nitrogen just rides over the warm air in my hand. Never actually touched me, so I didn't get a burn. But what happens if I pour it into my hand like this? Worst burn in my entire life. So you got to be very careful with liquid nitrogen. Well, you do want to see what it can do. So let's take a look at what it can do to some everyday things. What do we have right here? Well, that's a banana. And what's that right there? Well, that happens to be a banana split. And what do we have right here? Well, these are flowers. And don't we all love flowers? But that's a room temperature flower, right? Let's take that flower and put it in the liquid nitrogen. Now, what am I doing to the flower by putting it in the liquid nitrogen? I'm taking the energy out of the flower. And there's nowhere on Earth that's really the temperature of liquid nitrogen except the lab, right? The coldest place in Antarctica is like minus 190. So there's no place you can do this except the lab. We do this to everything. We want to know what happens to these objects when we make them this temperature. How does it act? We take the energy out. How does it act? So we take the flower out. You see it looks just like before, only now that flower breaks just like glass. Hey, this will tell you a lot about liquid nitrogen. What kind of balloon is that? Don't say hydrogen, a helium balloon. I'm going to take that helium balloon. I'm now going to roll it into liquid nitrogen. And as I do that, what happens to the balloon? Well, I'm slowing the helium down in the balloon. So the balloon gets smaller. It's no longer pressing on the inside with such force. And as the balloon gets smaller, it's actually more dense. So now it's a dense helium balloon that no longer floats. But I can take the balloon out, let it hit the floor like that. You'll note that the balloon starts to re-expand. And as it re-expands, it becomes less and less dense until finally the balloon can come up off the floor, re-expand, come right back up. Helium balloon lives again. There you go. Everybody likes that. Now, This will also show you a lot about liquid nitrogen, because remember, it goes 1 to 700 times its size from a liquid to a gas. So if I take it, pour it in a tube like this, you can see that as the steam pours out the top of that tube, you get that expansion coming out the tube. There's a lot of energy in that expansion too. In fact, I can use that expansion right now and that energy, try to cork it, it becomes a liquid nitrogen cannon. Watch out, Cap! We have right here the beds of nails. You can see these nails on your screen right now, and they're actually nice and sharp. Remember, it's all about Newton seeing that apple fall. Or here's an apple. Gravity pulled it down, hit the nails, but you can see all those holes in our apple. Those nails on our bed of nails are very, very, very sharp. But here's our experiment. We're going to take that bed of nails. We're going to put it right down here on our floor. Right down there. I'm going to take my body and lay it across that bed of nails. We then have a second bed of nails. We're going to put the nails down on my body. And then I'm going to take Michelle. Who's going to stand on it. And I'm going to be a Dave sandwich in between the beds of nails. Will I be okay? Well, I say we do the experiment and find out. Let's find out. So down here I go, on our bed of nails. And every bed needs a blanket. Mine just happens to be more nails.
What?
Right down there on my body. Yes. Oh, good. Now, I'm a Dave sandwich in between two beds of nails. And Michelle is going to add her mass to our beds of nails. And notice, I'm just fine. I'm perfectly okay. It doesn't really matter that Michelle is standing on me like this. I feel just great. No, I'm kidding. But you can get on down. Thank you, Michelle. At home, a big round of applause for Michelle. Now, we're going to take that off. And remember, our saying is in our show, that physics show, it's not magic, it's physics. So let's see what we mean by that. Because that looked suspiciously like a magic trick. But think about it this way. I weigh 200 pounds. If I lie down on a bed of nails with one nail, that'd be 200 pounds of force on the one nail. More than enough to pop the nail right through my body and kill me. Let's say my bed of nails had nails. There's 20 pounds of force on every one of those nails. More than enough to go right through my body and kill me. Let's say my bed of nails had 100 nails. 2 pounds of force on each nail. That hurts a little bit, but it won't go through human skin. You actually need about 12 pounds of force on a nail to go through human skin. Hey, I'm a scientist. I did the experiment. It was a bad day, but I can't help myself. So this is something really similar to me. Thin skin and filled with hot air, just a balloon. And this here is a whole lot of nails. Will this balloon bust on all those nails? I'd like you to predict, because there's not enough force in any one balloon, any one nail to go through the skin of the balloon. Here we have one with half as many nails, doubling the force in every one of those nails. Will the balloon bust this time? I say we find out. Do the experiment. Because, no, when I'm pressing, it still doesn't bust. Here you have a bed of nails with half as many again, doubling the force one more time. Will it bust this time? Well, it's our last one. So, of course, it's going to break. Just like that, how I would pop on a bed of nails without any nails. Now, for our last demonstration, we're going to ask Ryan to go ahead and lie down on our bed of nails. Thank you, Ryan. He's quite comfy, right? And now Michelle's going to bring over a couple objects. Thank you, Michelle. The first we have is our sign, right? That physics show. And if you like what you see in our video, please come and see us on our off-Broadway show when we're back and running, like everything else in Broadway. And it looks just like a guillotine, doesn't it? So we're going to put it right here on Ryan's neck, just like that guillotine. Next, we have a cinder block. And we're going to place this cinder block right on Ryan's rock-hard abs. Now, the last part of our experiment is the sledgehammer. So here's our experiment. Bed of nails, Ryan, brick, sledgehammer. When I break the brick, does Ryan live? No. What we got to do in life? You got to do the experiment. So, 3, 2, 1. Bust the brick. And Ryan is perfectly fine. Dave Mayulo here signing off.
I love how he's saying violence.
Wow. Oh my God.
Yeah, thank you all so much for watching that physics show. It's been running off Broadway for over 500 performances, and we're really glad we got to share the virtual version with you. So the presenter, Dave Mayulo, is going to be hopping on here in about 10 to 15 minutes, and he is going to be taking questions from you all. So if you want to take a couple of minutes and think about what in the show you want to ask him about, now is a great time to do that.
Okay, thank you very much.
Absolutely, and I'll be right here if there's anything you want to ask me or if you need ideas for questions. I'll be right here for the next couple minutes.
Can you give us some ideas of questions?
Absolutely. So if there's any particular demonstrations in the show that you want him to talk about some more, or like, for example, I heard a couple of reactions when he was doing the soda cans sinking and rising, so if you want a little clarification on that. Or you can also ask about how those are used in sort of bigger science demos, because those are all classroom versions. So there are things that he can do. You can talk about how you can take those versions and make them way bigger. Like, for example, with those density demonstrations, that refers to a lot of things that are like in the sea and in the ocean right now. So there's things like that. I'm curious, did anyone have a favorite demo from the show?
Yeah.
The nail.
The nails? Yeah, that one's a big hit, the breaking the nail on the stomach, which surprisingly doesn't hurt very much. But yeah, when I used to, oh, go ahead.
You tried it?
I have tried that one, and I've also been the person sandwiched in between while other people stand on top of it.
Oh
Oh my God.
Yep. So yeah, when we did the show, I was an assistant on it, so I would also do the fire extinguisher. I would hold the shield and get the fire extinguisher blown at me for the cart to go. Yeah, it's pretty wild.
Okay, now we discuss with students. In a couple minutes will be intermission.
Yep. Yeah. So we can.
At 1:05, you have to come to our class on a Zoom. Okay. From 1 p.m. to 1:05, we have a break, small break.
Oh, perfect.
And
Yep.
yes. And you have to come to Zoom same
Oh,
day, okay?
I'll rejoin the Zoom.
Yes.
Oh, okay, perfect. Yeah, so Dave will be back on at 1:05. And we can do questions then.
Thank you.
Perfect, absolutely.
Okay.
Okay. So questions. Just to remind you that Newton's laws are going to be on your state test, intermediate science next year. That I promise, always there. Density we did this year, but that thing with soda, he actually, back in the day, we had a lab where I would have a bucket and put the cans in, and you will see one is sinking, one is floating. What is interesting though, that when you buy the can of soda that is not diet soda, you do not realize how much sugar it has. So we usually have digital scale, and according to the label on a can of how many grams of sugar it has, we put that much of sugar on a scale so you can see how much it is in the can. The best thing for you to drink is water, okay? Because I wouldn't recommend diet soda as well. Water is the best. Okay. Carbonated, that just under pressure we have carbonate. And then it escapes. No, I think it's a fantastic show, by the way.
Yeah.
It's not boring for about 40 minutes a second.
Это самое. Подожди секундочку, откуда у тебя компьютер? Алкимен.
I was watching the Zoom.
Alcimena, I tell to everybody, save, put your computer in a box.
Окей, это самое. Давайте быстренько определитесь,
Кто не сдал работки.
Ирочка, вы обсудили какие вопросы? Потому что, ребят, мы это время оплачено, поймите, ваши родители за это шоу заплатили.
Хотя бы попросите, чтобы он рассказал applications of things you learned.
Хорошо, Ирочка, ты тоже можешь задавать вопросы. Дети, но я хочу, чтобы вы сейчас подумали над своим вопросом. И это серьезно, Ирочка, вот за эти вопросы, если у человека возникла мысль, значит он думающий. Вот поставили оценку за хороший вопрос. Давайте, дети, подумайте над вопросами. Женщины, подумайте над вопросами. Вы услышали меня, да? У умных людей возникают вопросы. Дети, я вам советую, когда пойдет это шоу, они все потихонечку возвращаются, сходить на Офф-Бродвее. Оно было просто amazing. Оно идет 1,5 часа там на Офф-Бродвее, но здесь вариант именно какой можно показать в классной комнате. А там на сцене, там, ну, это Офф-Бродвее, это не такой огромный зал, но территория, на которой они показывают эти опыты, огромная, в общем-то, большая. И это потрясающе. Это смотрится так, когда около тебя горит этот огонь, когда у тебя, ты сидишь первыми идут, и через буквально метр